Okay, sir. So last time we started discussing the Newton equation with multiple components. The component for radiation, component for matter, component for cosmological constant, and a component for curvature. Here, omega 0 is omega radiation plus omega matter plus omega cosmological constant, and omega I0 is epsilon I0 over epsilon critical 0. So we looked at initially a universe with matter and curvature, and then we moved on to a universe with matter and cosmological constant, and it was flat. So today we plan to look at, we plan to finish up our discussion of the matter and cosmological constant universe, and then I'll move on to a universe with matter, cosmological constant, and curvature, and the universe of radiation and matter, and finally a universe of everything. So the difficulty with doing everything to begin with is that this equation only admits analytic solutions in simple cases. So if you turn everything on, the only way to solve this equation is numerical. So we noticed that one possibility was a universe that ended in big crunches. So the universe expands, reaches maximum size, and then collapses and then contracts to zero size. So this is one possibility, and we solved the possibility for certain parameters in the universe with matter and curvature. Universes can also end in big chill, in which the expansion goes on forever. So we're going to see whether there are other possibilities, and in fact it turns out there are particular universes that may exist that don't even have a Big Bang. That it has existed forever, there's still an expansion, so strange things can happen as we proceed. So we looked at the universe with matter and cosmological constant. So the equation we're solving was omega lambda 0 is 1 minus omega m0 as a constraint, given that the universe is flat, and the frequency equation is h squared over h0 squared is omega m0 cubed plus omega m0. So this equation, we notice, has a solution with maximum at omega m0 over 1 minus omega m0 to the 1/3 power. And we noted that the sign, so this maximum applies in the case where omega lambda 0 is less than 0. The other possibility, where omega lambda 0 is bigger than 0, it has an infinite expansion. And we noticed that the behavior of the scale factor depends greatly on the sign of omega. So that's the universe for omega m0 0.9, and that's the universe for omega m0 1.1. So this universe undergoes a quick crunch. This universe keeps expanding forever and ends up cooling down. So let's look at this. We explored this case, the crunch case, in detail. That's the the universe would achieve its maximum at the scale factor. So now we're going to look at the second case of an expansion in further detail. Okay, so we have omega lambda 0 is positive, which means that omega m0 is less than 1, since the two have to sum up to 1. Then we notice that the two terms on the right-hand side with this condition are equal when A equals A m lambda, which is omega m0 over 1 minus omega m0 1/3. And we can solve for this expression by integrating, and we find that h0t is 2 over 3, 1 minus omega m0 log A over A m lambda to the 3½ power plus square root 1 plus A over A m lambda cubed. So at early times, when A is much, much smaller than A m lambda, the behavior of this expression is that A of t, scale factor, goes like 3½ square root omega m0 h0t to the 2/3 power. So the t to the 2/3 power is the characteristic power we expect for a matter-dominated universe. So this fits our assumption. At late times, when A is much, much bigger than A m lambda, however, A of t is A m lambda exponential 1 minus omega m0 to the 1/2 h0t. So again, this is what we expect. We expect that at late times, the scale factor increases exponentially because the universe is dominated by the cosmological constant. So we see that this expression is consistent with the things that we know. We notice that at early times, matter dominated, so it's increasing with the power law. At late times, it's increasing exponentially. So roughly speaking, this is our universe, in that the matter, omega matter is 0.3, omega lambda is 0.7 today. So this is positive, this is less than 1. At early times, we have this power law growth during the matter-dominated phase, and now we're in the cosmological constant-dominated phase, where we have this exponential growth. So let's compute when the transition happened between matter and cosmological constant domination. So if we solve for t0, we find that t0 is 2h0 inverse 1 minus omega m0 log 1 minus omega m0 over omega 0 to 1/2 plus 1 plus 1 minus omega 0 over omega 0 to the 1/2. So what I've done here is I've taken this expression, set A0 equal to 1, and that tells me that this is operative at the time t0. That's solved for t0. Okay, so it's just an algebra in order to get this expression. And we can simplify this a bit. This is 2 H0 inverse, 3, 1 minus omega m0, and combining the log, you get 1 minus omega m0 square root plus 1 over square root omega m0. So, if omega m0 is about 0.3 and omega lambda 0 is about 0.7, we find that T0 is 0.964 H0 inverse, which works out to 13.5 gigahertz. Now, if you compare this to Tm lambda, so again, you do a similar manipulation. You set A m lambda equal to the expression up there. You solve for the time with which that equality holds. You find that Tm lambda is 2 H0 inverse, 3 root 1 minus omega m0, log 1 plus 2, which is 0.702 H0 inverse, which is about 9.8 gigahertz. So this is very close to the age of the universe we observe. The universe we observe is about 13.8 gigahertz. And the time then at which the transition between matter domination and cosmological constant domination happened was 4 gigayears here. So it's relatively recent in the history of the universe. So as I was saying, this leads to the coincidence problem. So if you look at the dominant contribution to the energy density, initially, the dominant contribution, so if you're plotting omega lambda at time t versus time t, this looks basically like this. So for most of the history of the universe, omega lambda t is approximately 1. And in the early times, this was dominated by the terms like matter and radiation, and we happen to be sitting right here. So it's kind of coincidental, or perhaps maybe asks for explanation why in the history of the universe, when most of the history of the universe has omega lambda equals 1, why is it that we are at a time when omega matter and omega lambda are competitive? Why are these two numbers both order 1 just at the time we happen to be observing the universe? So this problem is called the coincidence problem. And if there's an answer, we don't know it. So now I want to move to my next universe with matter, curvature, and cosmological constant. So in this universe, we're going to have different possibilities. Omega 0 is bigger than 1, and omega lambda is less than 0. We have a universe which is infinite in space and finite in time. And if omega m0 is less than or equal to 1, and omega lambda 0 is greater or equal to 0, we can have a universe which is infinite in space and time. And we can also find more bizarre possibilities. So Einstein Einstein's static universe, in which we have a double dot equals 0, implies that 0 is minus 4 pi g Newton over 3 c squared epsilon matter plus the cosmological constant over 3. And this tells us then that lambda over 3 is 8 pi g Newton over 3 c squared epsilon lambda, which is 4 pi g Newton over 3 c squared epsilon m. So in this case, epsilon lambda is epsilon m over 2. And such a universe is finite in space and infinite in time. So we'll see that there are lots of possibilities, and even more possibilities will arise as we continue. Yeah?
Is that epsilon over 2, that last term?
Yes, epsilon m over 2. Okay, so we see there are already lots of possibilities when you turn all of these things on, and we'll find some more exotic possibilities now. So the list of possibilities will grow. As we turn on more and more parameters. Yeah.
Can you explain what it means to be finite in space with infinite?
So it means that the universe has a finite size, but it's always existed. Okay. So the way Einstein designed the static universe was a universe that was just sitting there, so it wasn't expanding. That's why he introduced his cosmological constant term in order to solve the equation such that the universe just sits there. So it's by design infinite in time, because at the time people didn't know the universe had a big bang. So that's a possibility here. So the equation we're studying is h squared over h0 squared equals omega m0 over a cubed plus 1 minus omega m0 minus omega lambda 0 over a squared plus omega lambda 0. So if omega matter 0 is positive and omega lambda 0 is positive, the middle term can either be positive or negative. Depends on how the sum compares to 1. So the sign middle term is plus or minus. So this is what gives us various possibilities we look for solutions to this equation. So for some choices, of omega lambda 0 and omega m0, we have the right-hand side is positive for small a. For small a, we have 1 over a cubed term here. So this term is the biggest term of all. So as a result, it dominates this term and this term. So as a result, for small a, you expect something positive. For if omega matter and omega lambda are positive, for example. So this is matter domination. And for large a, the right-hand side is also positive. So for large A, this term dies at 1 over A cubed, this term dies at 1 over A squared, and this term is just constant. So this term, if omega lambda 0 is positive, this term just sits there. So as a result, this is lambda dominant. But in the middle, between small a and large A, intermediate A, strange things can happen. So if this term, so if this term is positive, and this term is positive, and this term is negative, this can't be too negative. If this is too negative, then h squared over h 0 squared would be negative, which means h is imaginary, which doesn't make any sense. So for physical reasons, the term in the middle can't be too negative. But a negative value is not disallowed at the level of our analysis so far. Okay, so what can happen here is that suppose A is much, much bigger than 1. So in this case, we have h less than 0. So the universe is contracting due to low density. Lambda domination. And as the universe contracts, the curvature term here becomes dominant, and it stops maybe at A min, and it bounces again, it expands. So that's a possibility here. So we can stop at A min, and then bounce. And expand again. So I'm being a bit qualitative here. And the reason I'm being qualitative is there really isn't an analytic solution to this expression. You just need to look at the possibilities by solving this equation numerically. So in such a universe like this, with this bounce, it's possible to avoid the Big Bang. So the universe is getting bigger, it contracts, it bounces, and it gets bigger again. So as a result, it's only ever a minimum at A min. There's no A equals 0 state for the universe in this scenario. So that's a possibility. So this can avoid the Big Bang. So if we map out all the possibilities by solving this equation numerically, the space of solutions looks qualitatively like the graph I'll just draw. So this is omega m0. This axis is omega lambda 0. Minus 1, 0, 1, 2, 1, 2, 3. So all line. We've got this line here. This line separates kappa equals plus 1 from kappa equals minus 1. So this line corresponds to the sum of omega lambda and omega matter being 0. And then we have the line here at 0. And universes that fall below 0 here, so kappa equals to minus 1. Push another color. So universes that are here below this line are kappa equals -1. Universes above this line are kappa equals +1. So universes that fall below omega lambda 0, these universes undergo a big crunch. So up here, we've got some curve, and these universes are so-called big bounce universes. They're the universes that avoid a big bang. And here, we have universes that are so-called loitering universes, meaning the scale factor is merely constant for a long time before it starts to increase. So the universe is expanding extremely slowly, very close to this boundary. And eventually magma takes over and expands exponentially. The universes in the middle, between the big bounce and the big crunch universes, these are big chill universes. They're universes that expand forever and eventually become very, very cold. So the universes, so we can imagine, all these various possibilities by solving this equation numerically and seeing what happens to the scale factor. So the universe that we are in is a universe which is, okay, so we say a few words about this loitering universe. So we start with matter in as dominant carbon, and this tells us the scale factor increases as t to the 2/3. Then A is nearly constant for a long time, and then A expands exponentially as matter takes over. So how do we know we're not in a universe like that? Well, if we were in such a universe, we would find most galaxies would have the same redshift. They have a redshift associated to the scale at which the universe is loitering. And we would see nearly the same redshift for every galaxy we look at, and that's not what we observe. So as a result, we know that we're not that close to this boundary. So our universe is a big bound. Is not a loitering universe. If you look at the CMB, the cosmic wave background, we see evidence that the universe was much smaller and denser in the past. So we're not in a universe that was like this either. So we're not a big bounce universe. And we're seeing that cosmological constant is taking over from matter, so the universe we have is a big chill universe. So the reason we know we're not a big bounce universe is that if we were, to be a maximum redshift, Z max, which corresponds to the bounce -1, and galaxies which are further away than this, they'll blue shift rather than redshift, because the universe then was bigger, got smaller, and it bounced. So we don't see that either. So we know experimentally, observationally, that this is true and this is true. So the fact that lambda, the omega in lambda today is about 0.7, and omega matter today is about 0.3, tells us that we're in this big chill universe. So the big chill is characterized by infinite expansion and temperature falls off as the universe, the scale parameter, supercooling down. So this is the heat death of the universe that we have in forward. So as a result, if you look at this equation, so I just want to convey, look at this equation, you just solve it numerically, and there are lots of possibilities. So we should keep, so the way we do cosmology is we have a model. We look at the model tells us that there are these equations, we solve these equations, and we compare the predictions of the solutions to the equations to the observational data. That narrows down the parameters in the model. So the model here has several parameters. It has omega m0, and omega lambda 0, and h0. So you measure these things, and then we're able to determine what part of the parameter space we inhabit. So this is typically how people do various types of physics. So for example, using particle physics, there are parameters that correspond to masses of unknown particles. So you want to narrow down the range in which the particles' masses are, so you can actually go look for them. So you do this by inference. You find the results of suppose the particle has a mass m, and you see what the implications of giving the particle a mass m is, and that characterizes the behavior of other particles. So as a result, by looking at the behavior of the other particles, we're able to see whether the behavior you see in nature is consistent with the prediction that there's some other particle with mass m. If it's not consistent, you make some other prediction, you see where that leads you. So similarly, here, we're looking at the various possibilities corresponding to different values of the parameters. So in general, we have incomplete data. We're not working in classical mechanics where we have complete data about the initial state and final state of balls we throw at each other. That's no longer how we're doing science. We're doing science by making measurements, and we're seeing where those measurements are fitting in to the scope of some larger model that we've got. This is really the only way to operate when we have incomplete data and the inability to perform new experiments. Okay. So this is useful not so much in characterizing universes that don't make sense, but in characterizing how we do science. Okay? Okay, so let me say a few words then about radiation and matter. In this universe, the Friedmann equation looks like h squared over h0 squared is omega r0 over a to the fourth plus omega m0 over a cubed. So the two terms on the right-hand side, these are equal when A equals ARM equals omega R0 over omega M0, and this is 2.8 times 10 to the minus 4. So at A, much, much less than ARM, we have radiation domination. And A much, much bigger than ARM, we have matter domination. So we can solve, we find that A dot squared over H0 squared is omega R0 over A squared plus omega M0 over A. So we integrate this, we find that H0t is the integral dA over omega r0 over a squared plus omega m0 over a to 1/2. And this is an integral that we can do. And this integral turns out to be 4 ARM squared over 3 square root omega r0. 1 minus a over 2 ARM. 1 plus a over a rm to 1/2. So that's what happens when you look at the integral and do it. And we can study this result in various limits. Check that it behaves the way we expect. So for A much smaller than ARM, our result looks like A is approximately 2 square root omega r0, H0t to 1/2. And for A much bigger than ARM, our result looks like A is about 3/2 square root omega 0, H0t. So working in a flat universe, so omega r0 plus omega m0 is 1. And we see that there's a characteristic key to the 1/2 behavior that we expect for W equals 1/3, and a characteristic key to the 2/3 behavior that we expect for W equals 0. So it fits with what we've seen for a purely radiation universe or a purely matter universe. So we can compute the time at which the scale factor is equal to ARM, and this turns out to be 4/3 1 minus 1 over root 2 ARM squared over square root omega r0 H0 inverse, which works out to 0.391 omega r0 to 3/2 over omega m0 squared H0 inverse. And for omega r0 is 8.4 times 10 to the minus 5. Omega m0 is 0.3. Plug those numbers in. This is TRM is 47,000 years. So having a 3-component universe and having a scale factor here being such that A is much bigger than ARM, so it's a matter of domination, and much smaller than AM lambda, so it's not cosmological constant domination, that doesn't change our estimate of the age of the universe very much. We had previously the universe was 13.5 billion years old. That's corrected at 47,000 years. So it's a small correction. Okay? So for the fact that the universe was radiation dominated at early times doesn't really change our estimate for the age of the universe when you consider matter and cosmological constant. Okay, so we'll move on to a universe that has everything. And we want this universe that has everything to approximate our universe as best as we can. The way we do this that we measure parameters. We measure that today the universe is approximately flat. So 1 is very close to omega r0 plus omega m0 plus omega lambda 0, although we're indeterminate about whether the right-hand side is slightly bigger than the left-hand side or slightly smaller than the left-hand side, or they're exactly equal. We don't know, but they're pretty close. We know that. We know that H0 is approximately 70 kilometers per second megaparsec. And we measure the temperature, the CMP, and this is 2.725 Kelvin, which corresponds to omega in photons as being 5.0 times 10 to the minus 5. We know that the omega in the neutrinos, which are also relativistic, is about 68% of omega in the photons. So in total, omega radiation is 8.4 times 10 to the minus 5. We measure a baryonic component. So this is the stuff that forms gas clouds, the stuff that forms galaxies and stars. All that stuff is about 0.04. So the stuff you see, the stuff you interact with, is only 4% of the universe. So the rest, omega dark matter, is about 0.26. And the total omega matter is about 0.3. So this is scale factor W equals 1/3. This is equating the state parameter W equals 1/3. We equate the state parameter W equals 0. And we finally measure omega lambda 0 as 0.7. So those are the things in the universe. We see that 8.4 times 10 to the minus 5 is a very, very tiny number. And 0.3 plus 0.7 is approximately 1. So that's the content of this equation. We don't have enough decimal places in omega lambda 0 and omega matter 0 for radiation to make a difference, and we don't know these numbers with enough accuracy to compare, to see whether it's slightly bigger than one or slightly smaller. Those are the parameters we have for the universe. We know that because equating the state parameters for each of these things is getting smaller, radiation has equated the state parameter 1/3, matter has equated the state parameter 0, cosmological constant has equated the state parameter -1. We see that these different equating the state parameters correspond to domination of different components of the energy density at different times. So we begin with radiation domination. So first, we are radiation dominated. And the scale factor of the radiation domination would grow like e to the 1/2. And then there's a transition. Radiation and matter roughly the same when the scale factor is 2.8 times 10 to the minus 4. And then we're matter dominated. And here the scale factor goes like e to the 2/3. So this is TRM is 47,000 years. Then we go to cosmological constant domination. And this transition happened when A m lambda was about 0.75, and T m lambda was about 9.8 billion years. And here, A goes suppose like e to some constant times time. And this keeps going. And today, we're at T0 is 13.8 billion years. And at T0, we measure these values of the parameters. So those are our inputs. So given these inputs, we have our differential equation. H squared over H0 squared is omega radiation 0 raised to the fourth, plus omega matter 0 over A cubed, plus omega matter 0 plus 1 minus omega 0 over A squared. So this is, so the numerator here, H squared, is A dot squared over A squared, H0 squared. So this is a differential equation for the scale factor A. This is a freedom equation. So we solve this numerically for A, plugging in the parameters that we measured. So when we do this, we expect these different behaviors for the function A at different times, corresponding to when certain terms were dominant in the equations. So once we do this, we find a universe that, roughly speaking, looks like this. So I'm going to plot log A versus log H0t. So initially, this curve had a slope 1/2, corresponding to radiation domination. And then the slope became 2/3, so slightly bigger. And then eventually, after 2/3, so this is 2/3, and then it goes exponential. So this is exponential. This corresponds to radiation domination, the transition to matter domination. So there's some curvature here, so slightly curved as you go from one slope to the next, and then again slightly curved as you go from one slope to the next. It becomes exponential growth. So we see that the universe has dynamically evolved from one kind of behavior to the next kind of behavior, to the next kind of behavior, by solving this equation numerically. Okay, so this numerical solution is called a benchmark model. And we use this as our standard cosmology. We have some behavior that transitions between these different epochs in the history of the universe, and we look at the physics within this numerical solution to the Einstein equation. Okay, any questions? Why don't we take a break, and then we'll finish our discussion of this cosmology. Okay, we continue. So we've noticed that we were able to solve our differential equation and come up with a numerical expression for A of t. Once we once we have such a solution, then we can start describing the various things about the universe. So, for example, if you want to compute based on this model, so I'm plotting here H0 over C, dp T0. I'm plotting this on a log scale. And I'm plotting this against log Z. The benchmark model lets us solve this. It ends up looking something like this. And this contrasts with a matter-only universe, where this is matter-only. This is benchmark. And the universe which is cosmological. So we're able to see that behavior of the proper distance that we measure today changes depending upon the model we're studying. Similarly, if you plot H0 over C, dp te, also on a log scale, the behavior, again, is markedly different for the different theories. So, the benchmark model looks something like this. The matter model is like that. And the matter-only model looks like this. So, by mapping parameters to the benchmark model, we can determine the proper distance to an object today and the proper distance to an object when light is emitted from that object that we're seeing today. So, what does this mean? Well, in the benchmark model, what this means is that there's a maximum distance to which we can see. So the benchmark model, the distance to the horizon is 3.24 C over H0, which is 3.12 C times T0, which is 14,000 megaparsecs. So any further than 14,000 megaparsecs, you can't see. Because the light hasn't reached us yet. So, given this, we can solve for dp of T0 and dp Te, and notice what those plots tell us. So dp of T0, this asymptotes to the horizon, which is what we see in the plot. There's an asymptotic value in the benchmark model corresponding to the proper distance. dp of Te has a maximum value, and it corresponds to galaxies at redshift z equals 1.6, and at this maximum, dp of Te is 0.41 c over H0. So cosmologists ask essentially two related questions when they're observing something. How far away is that object we're observing, and how long has light taken in order to reach us? So these are slightly different questions because they're model dependent in giving us the answer. So we define what's called look-back time. So the look back time to an object is the time that we observe it today, minus the time the light was emitted. So for small redshift, the look back time is approximately z/h0. But for larger and larger redshifts, we need to look at these curves to determine what the look back time is. So for larger and larger values, of dp of t0, these correspond smaller and smaller values of the emission time. We're seeing distant objects. These distant objects that we're seeing, they correspond to the asymptotic value that we have for the proper distance today. So the most distant galaxies that we see, they have redshift around 6. So let's see what that means. The most distant galaxies we observe so the proper distance, dp t0, for such galaxies, works out to be 1.92c over h0, which is 8,300 megaparsecs. So the proper time, proper distance, when the light was emitted, is dp of t0 over 1 plus z. So this is 0.27 c over h0, which is 1,200 megaparsecs. So the most distant galaxies in the universe, when they emitted their light, they were 1,200 megaparsecs away. Now, they're 8,300 megaparsecs away. So TE here corresponds to 0.066 H0 inverse, which is 0.9 years. And T0 minus TE, the look back time, is 12.6 years. What this means is, the light to the most distant galaxies that we see, this light was emitted when the universe was just about 1 billion years old. It's been traveling for 12.5 billion years, and we're seeing it today. Okay? So the era of structure formation when the first galaxies formed, this happened when the universe was about 1 billion years old, and we'll discuss this later in this class. And this era of structure formation is an area which is not that well understood. So what people are doing now is they're looking for instruments to examine this era. So the square kilometer array, most of which will be built in South Africa and should be online next decade or so, that instrument is largely designed to probe this era of structure formation. And we'll see the first galaxies and the first stars forming with this instrument. So the difficulty is that, so there are two classes of big physics experiments. There are physics experiments in particle physics, and there are physics experiments in cosmology. And they're very different in character. And what I mean by that is the following. At a Large Hadron Collider, what you're doing is you're smashing protons together. When you're smashing these protons together, you're getting a bunch of junk, and you're wanting to extract a signal from this garbage you're getting from these collisions. So the way you extract a signal is you throw away most of your data. You impose certain cuts, certain filters on your data. And if your output of your experiment doesn't satisfy those filters, you just ignore it. And you look for particular cases in the data that do satisfy your filters, and you use that to throw these into some particles. So here, you can get away with throwing away data. In cosmology observations, you don't have that luxury. So the square kilometer array is going to be an array of a bunch of radio telescope dishes. And they're all pointing at the sky, and they're all seeing some angular part of the sky. What you want to do with these experiments is you want to correlate what one dish sees with what another dish sees. So you can't throw away data. Rather, you need to process the data in real time. And the problem is that, well, it's not a problem. The challenge is that once the square kilometer array is running, we should be expecting to see an internet worth of data every couple of days, every few days. You need to process this data in real time in order to find your signals. The technology for doing this doesn't exist. So the goal is that before the instrument's completed in the next decade or so, we figure out how to solve this problem in order that this instrument can actually teach us about this area of structure formation. So a lot of the investment in South African science is going into this radio astronomy effort. And there are plenty of opportunities here if you want to pursue this direction and analyze this data in order to learn something we don't really understand about the universe, this area of structure formation. But there are also other computational challenges involved that also need ideas in order to figure out how to process this data so quickly in real time. But that's the future of cosmology, understanding this period when the most distant objects that we see in the sky started to form, understanding the physics behind their formation. Any questions? Okay, so we've essentially looked at the Friedmann equation in various settings, and we've discussed how solutions to the Friedmann equation describe the universe today. And we've noticed that the scale factor can be solved under various assumptions. And depending upon these assumptions, you can be able to solve things analytically, or you need to refer to a numeric solution. In particular, we found numeric solutions in universes with matter, constant curvature that have other exotic features. And by looking at observational data, we're able to narrow down the parameter space in which the universe that we inhabit actually lives in this set of possible parameters. Given some measurements, we're then able to construct a benchmark model that we solve numerically, and this gives us an equation for the scale factor. And based on this equation for the scale factor, we're able to solve everything else we want to look for. So the goal then is to understand the parameters that appear in So to go into the benchmark model and understand the physics of these parameters. So how do we measure the parameters? We've also noticed that the universe that we experience is only 4% of the energy density. So we need to understand 26% of it, which is dark matter, and 70% of it, which is dark energy. So that's the next big challenge in understanding where these parameters come from. So in looking at dark energy and dark matter, there are physics questions. They're very fundamental in character. What is dark matter to begin with? And what is dark energy? Is the cosmological constant, something else? Where does it come from? How do we realize this within the parameters of the physical theory? Then we notice that our observations are circumscribed by physical considerations. In particular, we can't see infinitely far. We can't see to the infinite redshift. We can only see to finite redshift corresponding to the cosmic microwave background. Beyond that, the universe was very, very dense. As a result, light didn't propagate. So light was interacting with stuff, it bounced off stuff, and its mean-free path wasn't infinite, it was finite. So as a result, because of the density of the universe, we notice that the most distant object we encounter is the cosmic microwave background. And we need to understand the physics of the cosmic microwave background. Then we need to understand how structure formed. So how structure formed is a question with a couple of guises. The first is how galaxies, how stars and galaxies, I should say, form. And that's what SKA and other instruments will eventually teach us. But the question of how structure formed is also a question about how the elements form to begin with in order to make this stuff. And this process is a process called Big Bang nucleosynthesis. And much of this happened in the first 10 minutes. And much of this happened in the first 10 minutes because free neutrons, they're unstable. They decay to a proton or electron, and this decay process has a half-life of about 15 minutes. So the formation of all the elements in the universe happened very, very quickly in the history of the universe. Then we notice the observations that we make respect homogeneity and isotropy, which is good because those were our inputs, and we need to understand why this is the case. And this leads us to the idea of cosmological inflation in the early universe. So, understanding the Friedmann equation, which is what we've done so far, is really a first step, because what we've understood so far really forces us into addressing these questions. And the universe that we have seems to start at a Big Bang, and we don't really understand the structure of Big Bang singularity and what happened there. So all of these questions these questions, some of these questions have more or less complete answers. Some of these questions we're still totally in the dark about. So that's sort of the subject of the second half of the course. Okay. So tomorrow we'll start going over the exercises for this chapter, And then starting next week, we'll systematically start addressing these other questions. So starting next week, we'll have the second lecture for the course, Dr. Jeff, and he'll guide you through this discussion here. Any questions? Okay, I'll see you tomorrow then.